All right, so yesterday we learned a concept where I had a box or an object that was moving towards the right. So it's like horizontal SHM, right? That's what we did yesterday. Today, I'm going to do something similar, except it's going to be vertical. And whenever I'm doing anything that's vertical in physics, there's going to be gravity. So just keep that at the back of your minds. And yeah. So this is our plane, and I have a spring. I have a spring, and I have an object here. I have a mass. And this mass obviously is going to have weight, right? It's going to have some kind of weight. Now, when I have the spring and I have the weight, it's pretty obvious that this spring is not at its original length, right? Because I have weight, right? So the spring is not at its original length, meaning there was some kind of extension, right? That's why I'm going to write E over here, because I know that there was some kind of extension. By the way, I'm not using speaker these days, so if you ever hear that someone's mic is on, like, I don't know, so just go ahead and tell him to turn off the mic, because I cannot identify it. Now, you know that because I have weight here, and this weight is pulling the string down, there's obviously going to be some kind of force, right? There's going to be a force in the opposite direction, because when I leave this, when I release this, it's going to go up. Now, this force is what I like to call Fe. I'm going to call this Fe. Now, okay, so W is equal to this Fe. Now, I have a question for you guys. Whenever we learn about springs or strings, what is the formula for force? What is the formula of this F? Can anyone remind me? Basic extension and constant formula. Come on. Who knows? Yeah, Kx. I can also write it Ke, because x is technically the displacement or the extension. Let's go with extension because displacement is a vector. So I'm going to write Ke. Now, I can say that W or mg is equal to Ke, right? So this mg came from this W. I hope you guys understand this fact, that W and Fe are equal, and I know that Fe is Ke, and I know that this mg is W. Let that sink in for a while. Okay, I hope that sinked in. Now, we're going to add something to this thing, right? I'm going to make another line, and I'm going to make another line here, and this spring right here, we're going to extend it even more, okay? Now, I have, this is SHM Phys. Okay. All right, so our spring has extended more, right? So here goes our spring. Now this is the weight, right? Now, I have allowed this spring to extend even more. Now, let's say that, this point right here is somewhere over here, right? Let's say this is the point. And obviously, I know that this box, it has displaced down, towards the bottom. So I can say that this is x, right? This is x. So this is the displacement. Okay, now I know that F is equal to Kx, right? Let's write that down. I know that F is Kx, right? Or Ke. Let's go with Ke. So I know that force is Ke, but now you can see that it's not just E. It's not just the old extension, right? It's not just the extension. I have X as well. So can I say that F is now Ke plus X? Let that sink in, because this is where students get confused. Okay, where did X come from? Tell me one thing. At this point, okay, let's call it point X, right? Let's call it point X. Let's say, okay, let's go with point A because this is X2. So this is point A. Now I know that this point A is already a point for an extended spring. I already have an extension here. Now, it's not just my E. I have X too. So can I say that my total extension is going to be E plus X? I hope that made sense. Now, I know that there's going to be a force which is acting upwards as well, right? So tell me one thing. Okay, now this is a question for you guys. When I extend the spring, right, and I reach a point, okay, I'm going to answer your confusion in a few seconds. Just give me a second. Okay, guys, a question for you guys. I have the spring and I am extending the spring. Okay, let's imagine that this arrow, this is my spring, right? So I am extending the spring. Now tell me one thing. Is my box gonna go up or down? Is it gonna go up or down? Tell me that thing. Come on, guys. Is it gonna go up or down? Exactly, up. So can I, Wahaj, come on, it's gonna go up. It's a spring. It's a spring. It has that force which is upwards. So I know, I can say, in fact, that this is my resultant force. So I know that my resultant force is gonna be towards this direction. This is just a side note that I wanna make before I do the next thing. Now let's answer the questions. Let me read your questions just a second. So this is F resultant. And I also know that there's an FE over here. This is, this is our F, right? This is F. Now, give me 1 second. Let me read the question. Okay, so Eliza and US man, they're confused mean extend plus original length. Okay. Now I'm gonna put some effort into this, so please pay attention. Now, imagine that this was my spring. Just give me a second. Come on, just give me a second and listen to this, okay? Now pay attention. Look at this. First of all, Eliza, listen. Total extension, it's not just any final. It's final length. It's final length minus initial length. But over here, I'm talking about extensions. This is extension 1, and this is extension 2. Your final minus initial, that's length, right? Now, let me tell you one thing. Look at this. This is my spring. Okay, let's say this is a spring before I attached any weight. There's no weight here, right? There's no mass. Now, pay attention. There's no mass, right? Okay, so there's no extension, right? So it has some kind of length, right? This is L. This is L1. Now, I have attached a box over here, and this is L2. Now, answering Eliza's question, if you want to find E, what would you do, Eliza? Tell me. This is a question for Eliza specifically. If I want to find E, extension, what do? I have L1 and I have L2. What would you do if you want to find extension? Come on, tell me. It's just a small answer. Can you do it? Hey, Eliza, are you there? Yeah, L2 minus L1. L2 minus L1. So E is L2 minus L1. So this is my extension. Now, look at this. I have one extension. Now, I have pulled this thing. I mean, the same spring went even down, right? It went even below, right? So imagine that at this point, the extension here is caused by the weight. Now let's imagine that over here, I have somehow displaced it down. So tell me one thing. Let's imagine that this is, okay, I know this might be a bit confusing, but bear with it. Now, this is L3, okay? But first, just give me a second. So if I want to find X, what do I do? Now imagine that this is initial length and this is final length. Okay, Eliza, what would I do if I want to find this extension, right? X is also an extension. What would I do? This is my initial length and this is my final length. What should I do to find X? Can you please tell me? No. L3 minus L2, right? I'm answering your question using your own logic. Now, pay attention. Over here, I'm not talking about lengths at all. I'm not talking about length at all. E, this is my first extension. When I had W over here, right, I got an extension. Now, this thing has extended even more. This is extension number 2. So I can say, I'm just going to write specially for you guys. Let's say this is extension 1. This is extension 1, and this is extension 2, right? And I know that the formula is force is equal to constant into extension. Now, if I want to add, this is my final version of my spring. Now, if I ask you, what is my total extension? Eliza, tell me, what is my total extension? If this is extension 1 and this is extension 2, what is going to be my total extension? Can you please answer this question? Exactly. So that's why I did E plus X. So I hope no one is confused about this. So forget length. We're not even talking about length at all. It's just extension. Okay, now F resultant is upwards. I know that there's a force F over here and there's weight W over here. So if I want to find this F resultant, what would I do? I would obviously subtract F. Now, this is a very interesting thing. When I was teaching centripetal force, now pay attention, when I was teaching circular motion, a lot of students, not a lot of, several students asked me, why can't I do W minus F? Well, tell me one thing. What is the direction of my resultant force? Upwards, right? It's upwards. So obviously, my bigger force is going to be the one that's in the same direction as this, right? So F is the bigger force in this scenario, for this case. So if I want to find F resultant, what would I do? I would obviously go ahead and I would subtract this with W. So now I'm going to do this. Check this out. Okay, E plus X minus W. Does this make sense? I subtracted F with W to find F resultant, right? Okay, now I know that W, isn't this W2, right? So W is equal to KE. Now I'm going to substitute this into this, and this in turn is going to give me KE plus KX minus KE. Now I'm going to get something here. KE and KE, they're going to get canceled out. And I'm going to get F resultant. Now, tell me one thing. What is F result? What is the formula for force? Like the basic formula. Can anyone remind me? What is the formula for force? Okay. Yeah, MA. It's MA. So mass into acceleration is equal to KX. Do you see acceleration here? Do you see displacement? You know that acceleration and displacement are always in opposite direction, right? So I can write minus here. I can add a negative sign here. So I'm going to add a negative sign here. And this is going to give me A is equal to minus K over MX. Now there's something I have to mention here. I'm going to write a small statement, and this is going to make sense. A is up, X is down. You know that this is my resultant force and it's upwards, and I know that acceleration is obviously, since it's moving upwards, so it's going to have an acceleration that's also upwards. That's why A is up and X is down, and that's why I wrote here MA is equal to minus KX, because I know that A and X, they are vectors. I hope no one has this confusion. And now check this out. Doesn't this resemble A is equal to minus omega square X, right? It's literally the same. So I can say that omega squared is K divided by M. And just like the last time, now we're going to find the formula for time period, and we're going to find the formula for our frequency. Now, please note this down, and I'm going to tell you one more thing here. Okay, so as you're noting down, This is K over M, right? So if I use this formula and I say K over M, now if I make K over M the subject in this formula, I'm going to get G over E, right? So I know that K over M is equal to G over E. Now let me make all of this smaller, and this is going to give us some space. Okay, we have some space here. Now, I know that omega squared is not just K over M, it's G over E. So I'm going to write something here. Okay, just a second. Let me separate these two things. Okay, I'm making a little border. Okay. Omega squared is G over E. Now I know that omega, okay, can anyone remind me what is the formula? What are the two formulas for omega? Come on, let's see who can remember. Basic stuff. Come on, guys. What is the formula for angular frequency? Can anyone tell me? Yeah, 2 pi f and 2 pi over t. Amazing. So let's go with 2 pi over t for starters. Now, 2 pi divided by t squared is equal to G over E. Now, I want to make t the subject. So 4 pi squared divided by t squared is equal to G over E. Now, I'm going to bring t squared to one side, and I'm going to move all of the stuff to the other side. Now, this E is going to come up here, and G is going to go down. So 4 pi squared E divided by G. Now, since this is a square, I'm going to do an under root, and finally, I'm going to get under root. Okay, first of all, I have to write 2 pi. I hope everyone knows that the under root of 4 pi squared is 2 pi. So 2 pi under root E divided by G. That's what we got. Now, I know that E is more or less a constant. And I know that 2 pi is also somewhat constant. Now check this out. I can say that T is inversely proportional to the under root of G. Now this is something, I know, for people who don't like physics, this stuff might have been like boring. Now, this is where it gets fun. I know that G is the gravitational force, right? So this says that if my gravitational force is high, my time period is going to be small. And if my gravitational force is small, my time period is going to be high. Now tell me one thing. Okay, let me make two circles here. Let's say this is Earth, and let's say that this is Moon. Which one of these has greater G? Which one of these has greater G? Which one of these has larger value of G? Earth, obviously Earth. So it has a greater G. Now, if my G is greater, can I say that it'll have smaller T? Now, this is not for the planet. This is for this experiment that I'm doing above. Now, I know that on Earth, if I'm doing the same experiment in both of these places, this result is going to give me smaller T. So I'm going to get smaller T. Now, this has smaller G, but this is going to give me greater T. Now, isn't this cool? If you do the same experiment, literally using the same conditions except the G is different. Now, if you would do the same experiment, if you would do the same experiment on Moon, your time period would be larger, meaning it would have slower oscillations, right? It'll have slower oscillations, and it's going to be easier for you to find the time period. Well, obviously, you're not going to go to Moon just for one experiment. So let's write a little heading like Moon and Earth. This is Earth and this is Moon. Okay, now that's a lot of stuff. So note this down and tell me when you're done. I'm not going to erase this. I'm just going to write another thing for frequency. Okay, now let's do the same thing we just did, but okay, Ima, now look at this really carefully. I know that omega square is k over m, right? But it's not just W is equal to KE. I also know that mg is equal to KE, right? So if I make K over M the common here, if I take K over M on one side, I'm going to get G over E on other side. So K over M is equal to G over E. So I can substitute K over M with G over E because that's what we actually need. That's what we need to prove. So I hope that makes sense. Okay. Oh, just a second. Let me move this thing. No problem. All right. So now we're going to make another formula over here for frequency. Now I know that omega squared is also 2 pi f. So 2 pi f squared is equal to G over E. I mean, is it G over E? Yeah, it's G over E. Now it's going to be 4 pi squared f squared G over E, and I'm finally going to get f is equal to 1 over 2 pi under root G over E. Yeah, that's what I'm going to get. For frequency, you can see that it's a completely different relation, right? So that's it for the first part. Now, yeah. Okay, so when you're done noting till this part, tell me. Okay, so US man, listen. First of all, I don't know what's your name, so whoever you are, listen. This chapter has a lot of derivation, and that's what makes this chapter tricky. And maybe for some, this chapter might even be a bit boring. But there's also, yeah, there's going to be some fun stuff coming up ahead. So yeah, it's a little portion, but there's going to be a fun part. Bro, this is just the way SHM is, man. But in reality, the applications of SHM are amazing. I mean, if SHM didn't exist, a lot of stuff couldn't even have been, done. Okay, has everyone noted it down till this part? And by the way, make sure you practice it. You practice this at home. If you're literally like, okay, so I have the screenshot. You looked here, you looked there, you looked here, you looked here. That's not going to be enough. You have to practice. No, there's not going to be any integration here, man. No, it's in physics. You're not supposed to know integration. It's just for those who do math. Okay, I am clearing this up now. All of you know that we've been doing experiments with one spring, right? We've been doing experiments with one spring. But now, okay, so let's say I had one spring back in the day, but now I want to add another spring, right? I want to add another spring. Now, let's remove this and let's place another spring here. So this is springy 1, and this is springy 2. Okay. Now I'm going to use some connectors to connect the mass. Okay, now what we want to find here is how does time period vary with the number of spring? So let's say, when I had just one spring, my time period was, let's say, 5 seconds. Now scientists, it was kind of hard for them to repeat the experiment every time. So if they use the same springs, they created a formula that's going to allow them to find the time period, even if they theoretically find it out for 100 springs. You don't even need to do the experiment. Now let's see how we can find that formula. Now I know that time period, according to what we did before, is 2 pi under root E over G. That's the first formula, right? The one we just found out before. Okay, now tell me, when I'm using 2 springs, what's gonna change to how is my extension gonna change? Is my extension gonna increase or is it gonna decrease? And by how much is it gonna decrease? By half, by quarter, by, by thrice? How much is my extension gonna change when I use 2 springs instead of one spring, like I did before? Can anyone answer this question? Exactly, half. So what I'm going to do here is I am going to divide extension by 2. So let's use a red marker, and I'm going to divide this by 2. Now I can write the same thing like this. So 2 pi under root e divided by 2g. Now I want to take this 2 out, right? Because I want to make this common. So I'm going to take this 2 out, and I'm going to get 2 pi. Okay, I'm going to get 1 divided by under root 2. Don't forget that this under root is for each and every number. So if I take this out, it's going to be the same thing. So don't get confused. Now this is going to be 2 pi under root e over g. Now I know that this is literally t, right? This thing right here. Let me use a different color. Now this thing right here, this is t, right? So I can say that this is t. So this thing is not going to be t anymore. This is going to become tn. Now pay attention. Let's say I had 3 springs. Let's say I had 4 springs. Let's say I had 5 springs. This number would be the number of springs. Let's say, you know, I did the same experiment for, I don't know, like a 50 springs. What I would do is I would divide extension by 50, meaning I would write 50 over here. So let me use a black marker. Okay, so let's say I'm doing the same experiment for 50 springs, right? And this is like T50, right? Now I'm going to get back to this. First, let's finalize the formula for 2 springs. So the T we found here is 1 over under root 2, 2 pi under root e over g. If anyone has confusion about this, do tell me. Now I'm going to show you that general formula that we're going to develop now. Okay, now let's say I have Tn. I have n number of springs. So I can write this formula right here as 1 over under root n 2 pi e over g. Now I clearly said to you guys that this thing is t. So what I can do here is I'm going to take Tn. I'm going to do 1 over under root n, and this is going to become t. So let's say you want to find the time period for if you are using the same number of springs. I mean, if you're using the same type of springs, right? Let's say I want to find the time period for 20 springs. What you're going to do is you're going to take this 20, and you know it's going to be T20 and 1 divided by under root 20 multiplied by whatever time period you had. Let's say my time period was 5. So by multiplying this, I can find my time period. That's what this formula is used for. Does anyone have confusion in this part? Tell me, please. Oh yeah, and n is number of springs. So n, I'm glad. So n is number of springs. N. Okay, that's amazing. Now I'm going to make a borderline here in the middle because we're going to do a comparison. Yeah, that's what we're going to do now. So what if the springs are actually getting attached to each other? So I know that one spring is already, springy. Now, if I use another spring and I attach the 2 springs, what's going to happen now? That's what I'm going to teach now. So I have this thing right here. And so this is my first spring. This is the first spring. Now what I did was I attached the second spring with the first one. So let's say this is where we attached them, and I want to know what happens to the time period now. These are the same springs, by the way. First of all, tell me what's going to happen to my extension. Is it going to increase, or yeah, it's going to double? That's a good answer. It's going to double. So I can say that E is going to get multiplied by 2, and it is being divided by G. So 2E divided by G. Now I'm going to do the same thing I did for this, except this time it's going to be under root 2 instead of just 1 over under root 2. So now it's going to be under root 2, 2 pi under root e divided by g. That's the extension, that's the time period if I used 2 springs. Now I can find this general formula, Tn springs, right? Under root n into t. So if I want to find, the time period, if I use like 100 springs, I could literally put 100 into this, and I could multiply this by my time period, and I could find the answer. Okay, is this clear? Note this down. When you're done, we're going to do the next thing. By the way, this kind of relates with AS2. So, okay, what we're going to find through this. Okay, so in the paper, they might ask you that. So, okay, just what I said. Let's say I have 5 springs. Let's say your time period. Okay, let's do a really cool thing. The time period was 5 seconds. Examiner says you are using, okay, I'm going to try to remove this. Give me a few seconds. Time period is 5 seconds, right? I'm using 5 springs now. Now, if you didn't know this formula, what would you do? I mean, you literally have the time period and you have the number of springs. There's literally no way for you to find out the new time period because you don't have extension, you have nothing. What you're going to do is you're going to, find T5 under root, 5 into 5. So the new time period is going to be under root 5 into 5. So the relation between them is so basically more number of springs you have in this scenario. I mean, more number of springs you have, greater your time period. So if you have more springs, your time period is going to increase. But in this scenario, if you have a lot of springs, your time period is going to decrease. I hope you understand this. So you can see we have the t here and we have the number of springs here. So t is constant and this t is what we're going to find. So if my n is great, Tn is going to be small, right? But in this scenario, if my n, oh, lol, I literally erased this. It was Tn is equal to under root n into t. But in this scenario, if my n increases, t is going to go up as well. I hope that makes sense. And I'm clearing this in 5 seconds. Okay. Now, can anyone confirm? Can everyone confirm? Is everyone getting that static noise, or was it just one student? Do you hear any kind of static noise at all? Okay. Okay, I'm going to enable the noise cancellation in just a second. Okay, what about now? It should be gone now, unless the noise cancellation betrayed me. Okay, that's amazing. By the way, the time is up, so we're going to have to do another meeting. We're going to study a lot of stuff today, so I mean, you're going to have to do some nice revision. Okay, so I'm ending this meeting and I'm sending you the new link. Thanks. Okay, sending you the new link.